Slope fields. The objective in this lesson is to use a slope field to represent the solution of a first-order differential equation. Slope fields are graphical representations of differential equations. They give a visualization of the parallel curves that solve the differential equation. Notice down here on my screen are a bunch of different slope fields. These are visualizations of the solutions to differential equations. So from these graphs, I can tell that the solution of the differential equation in this one would be circular, while in something like this it would be linear, and in something like this it would be quadratic. There are a bunch of different types of slope fields because there are many different types of solutions of differential equations. We use slope fields when we cannot solve the differential equation analytically. It gives us a good visual of the solution since we can't solve it in another way. It is an estimation technique. To sketch a slope field, you'll notice if the differential equation is dependent on just one variable or both x and y. Then you'll plug in points to evaluate the derivative, and you'll graph little line segments that have the slope value found in the differential equation dy dx. Let's take a look at some examples. 1. Sketch the slope field for dy dx equals 2x on the axes provided. So to do that, we want to think about, first, what is the differential equation dependent on, x, y, or both? Noticing that in our differential equation, we only have x. So when we think about what are going to be the slopes, we only have to think about when the x coordinates, what the x coordinates are. So when x equals 0, our derivative dy dx, which remember means slope, is 2 times 0 instead of 2 times x, which makes 0. So on my graph, anywhere x is 0, such as 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, I have a slope of 0. So notice what I'm drawing is a little horizontal line segment because a horizontal line has a slope of 0. So it's important to remember that dy dx means the slope, and therefore we are graphing a field of slopes. Let's continue to put little horizontal tangents everywhere else that x equals 0. When x changes, the slope is going to change. So how about when x equals 1? What do we get for dy dx? 2 times 1, which is 2. Now if I think about a slope of 2, that would mean that going up 2 and over 1 is the type of slope that I would get. So I want to be parallel to that type of slope. So positive and a little bit steeper than if it were to be up 1 and over 1. And that's going to be everywhere that x equals 1. I draw a little line segment that has a slope that looks like it's approximately positive 2. Now remember, this is an estimation technique, so my little line segments don't have to be perfect. But if the slope is positive, that should look like a positive slope. If the slope is negative, it should look like a negative slope. As the slopes get larger, they should look steeper. Let's do x equals negative 1. dy dx equals 2 times negative 1, which is negative 2. So if this is positive 2, over here where x is negative 1, I should be getting negative 2, which should look symmetrical to this, but negative instead. So everywhere up and down where x is negative 1, the little line segment should have a slope approximately negative 2. How about when x is 2? What happens? dy dx is 2 times 2, which is 4. Now, that's going to be hard to draw, but keep in mind that it's still a positive slope and it should be steeper than positive 2. So as I go to the right, I'm going to make it look steeper than what was next to it. And everywhere, up and down, where x is 1, it should be a little line segment that looks a little bit steeper to the one to the left. Now, x is negative 2, same idea, but steeper in the negative direction. Now, I don't have to write down my work for each one, more so it's a thought process. As x gets greater, this slope gets greater. So these little line segments should be steeper. And then eventually I fill in the rest of the field. Going to the left, steeper, but negatively steep. And then I get an idea for what the solution curves could look like. So first, I'm going to sketch 3 particular solutions for the following initial conditions. First, it's going to be with the initial condition 0, 0. So I'm going to go over to where x, y is 0, 0. And then I'm going to follow my slope lines to the left and to the right. Now, first, the slope is 0. So moving to the right or to the left, it should be fairly flat. But as I move to the right, I notice the fact that the slopes are getting positive and they're getting steeper. So I want to follow those little line segments, make sure that I'm either touching it so it's tangent or parallel to it because it has the same slope. I also go to the left and I try to follow approximately where those little curves are directing me to go. That's the solution curve for the point at 0, 0, the initial condition 0, 0. Now, what if my initial condition was 0, 1? How would that look differently? Let's go up to 0, 1. Notice that the slope is 0 there, but as I go to the right, the slopes are positive and get steeper, and as I go to the left, the slopes are negative and get steeper, and therefore it looks like that. One more solution curve, 0, negative 2. If I were to start down here, going to the right, again, it is positive, and going to the left. Notice that I'm not crossing through any of them like that. That would be going against the slope, and that is not correct. So see how this slope field gave us a visualization of the solution curves to the differential equation dy dx equals 2x. While this differential equation is linear, when I take a look at the solution curves, they look quadratic. It's a parabola. So to describe the possible solution curves, I would say that they look quadratic, like y equals x squared. Number 2, sketch the slope field for dy dx equals 2 times y on the axes provided. Notice this time the derivative is only dependent upon y. So now when I think about how to find the slopes of my little line segments, I'm only going to worry about what y equals. Up here, I only had to worry about what x equals. So I'm going to think about when y equals 0, what's the slope going to be? dy dx equals 2 times 0, which is 0. So now when I'm graphing my little line segments, it's everywhere that y is 0, which is here and here and here. All along the x-axis is where y is 0, so my slopes have to be 0. How about when y is 1? Then dy dx is 2 times 1, which is 2. Now notice I'm doing the same thing that I did up here, except I was using when x equals 1, and now I'm using when y equals 1. So now I'm looking at when y is 1, I'm going to put a little line segment that has a slope of 2, and it's everywhere that y is 1, which is to the right and to the left at y equals 1. Similarly, when y equals negative 1, I get a slope of 2 times negative 1, which is negative 2. So now I have to think about the symmetry of this, but with a negative slope down here where y is negative 1. Now it's not exact, remember it's an estimation technique, but I'm doing my best. We continue and think about, well, what about when y is 2? Well, as y gets bigger, this slope value is going to get bigger, and therefore my tangent lines need to have a steeper slope. Now I call these my tangent lines because they would be tangent to the curve if I had the curves here. And steeper, going more positive, and very, very steep. I'm trying to do the best I can, but again, it's an estimation technique to get an idea of what the curves might look like. Now, as I get more negative, again, these get more negative, and that's, of course, only in the y direction, moving up or down. Now let's take a look at some of the solution curves. So here, sketching three particular solutions, if I start at 0, 0 for the initial condition, when I go to the right, I notice that the slope is always 0. So to the right and to the left, it's just a horizontal line. That doesn't give me much of a clue about the possible solution curve descriptions, so let's take a look at some other particular solutions that I can graph. At 0, 1, it's a positive slope, and as I move to the right, the slopes get steeper, and as I move to the left, the slopes get less steep, but as I move down, really, this one's dependent going up and down, as I move down and get closer to the x-axis, the slopes become close to 0, very much like a horizontal asymptote. Let's try what it looks like at 0, negative 2. Down here, that's a negative slope, and as I follow down, it gets steeper, but as I go up, it gets less steep, and again, getting close to the x-axis, the slopes have to get close to 0. So what do these curves look like when we describe the possible solution curves? If we look at the pink one, we can tell a little bit more clearly. These look exponential. So I would describe these possible solution curves as exponential, like y equals e to the x. This one that's in the negative y area would be like y equals e to the negative x.